How many edges can you add to a graph before a clique becomes unavoidable? Turán's theorem gives the sharp answer. For n vertices, the densest graph that can still avoid a kk is the balanced complete k-1 partite graph. Add any more edges, and a kk must appear. First, a reminder. A clique is a set of vertices where every pair is connected by an edge. A K3 is a triangle. A K4 is 4 vertices with all 6 possible edges. In general, a KK is a fully connected group of K vertices. The first famous case is K equals 3. Mantle's theorem says that an n-vertex triangle-free graph has at most floor n squared over 4 edges. So if you cross that number by even one edge, a triangle is forced to appear. Turán's idea is to build the densest graph that still avoids the forbidden clique. To avoid a kk, split the vertices into k-1 parts. Put in every edge between different parts, but put no edges inside any one part. Why does that avoid a kk? Because a clique can use at most one vertex from each part. If you choose k vertices but there are only k-1 parts, then 2 chosen vertices land in the same part. They are not connected, so the chosen set cannot be a clique. The number of edges in this balanced complete multipartite graph is called Tr of n, where r is k-1. If the parts are p1 through pr, then Tr of n equals 1/2 times n squared minus the sum of the squares of the part sizes. When r divides n, this simplifies to 1 minus 1 over r, times n squared over 2. Here is the concrete case n equals 9 and k equals 4. We split the 9 vertices into 3 parts of 3 vertices each. We connect every pair of vertices in different parts. This complete tripartite graph has 27 edges, but it has no k4. Now add just one extra edge inside a part. Take the 2 endpoints of that new edge, then pick one vertex from each of the other 2 parts. All cross edges were already present, and the new inside edge completes the missing connection. A k4 appears. The balanced condition is essential. If one part is much larger than another, moving a vertex from the larger part to the smaller part creates more cross edges. So the maximum edge count occurs when the part sizes differ by at most 1. The proof idea is, suppose a graph has no kk but has as many edges as possible. One can transform it without losing edges and without creating a kk into a complete multipartite graph with k-1 parts. Then the edge count is maximized by balancing those parts. That graph is the Turán graph. So the theorem can be read as a density threshold. Below the threshold, a graph might avoid kk at the threshold. The extremal example is the Turán graph. Above the threshold, avoiding kk is impossible, so a k-clique must exist. This theorem is a gateway result in extremal graph theory. It connects a global measurement, the number of edges, with a local structure, the existence of a clique. The same philosophy appears throughout combinatorics, Ramsey theory, and network analysis. The takeaway is simple. To avoid a k-clique for as long as possible, use k-1 balanced parts and all cross edges. That is the last safe graph. Add any more edges than that, and Turán's theorem guarantees a kk.